In this video lecture, we're going to discuss combinational logic circuit design. So what is combinational logic circuit? A logic circuit, it accepts a set of inputs, process it, and give us a set of output. So input, process, output. This is an example of combinational logic circuit, wherein we have three inputs, which are A, B, and C, and we have logic gates that process our inputs, and we have two outputs, F1 and F2. In this example, we have two outputs, and for each output, we have a sub-circuit. So this sub-circuit is for F1, and this sub-circuit is for F2. So therefore, if we have multiple output, we need to have multiple sub-circuit to form the bigger circuit. So how do we design our combinational logic circuit? So in designing, it's like solving a math problem. So we start with the problem description. So we need to know what is asked, what should be the behavior of the circuit. And then second step will be determine the number of inputs of the circuit and the number of output. Then after determining the input, the output, the behavior of the circuit, now we could define the truth table. So after defining the truth table, we could define the Boolean equation of the circuit. After determining the equation, we may now simplify it so that when we implement the Boolean equation, so it will have a lesser number of variables, lesser number of terms. And then after simplifying our Boolean equation, we draw the circuit and then we implement it, determine if it's correct or not. So let's have this example. In this example, we're going to have two outputs, Y and Z, and then we're going to count the number of ones in a three-input circuit. Okay, so this will be our number of inputs, 3, output, 2, Y and Z. And we could now draw the circuit or the truth table based on what is asked and the number of input and output. So this will be the truth table. As you can see, the number of ones corresponds to the binary equivalent of a decimal. If it's 1, it's 0, 1. If it's 2, it's 1, 0. If it's 3, it will be 1, 1. Okay, so we just count the number of ones in binary form. So after creating this truth table, now we're going to simplify it. Okay, but before that, we need to determine the equation. So these are the equation of Y and Z output. And then using Carnot simplify it. So this will be A not BC, AB not C, ABC not, and ABC. And then we're going to group our minterm list. So we have three groups of 2. All have exclusive 1. So therefore, all groups will be part of the final answer for Y, final equation for Y. Okay. And then determine each term of the term corresponding to the group. So this will be the final equation for Y. BC plus AC plus AB. Now for Z, let's plot our minterm. A not B not C, A not B C not, AB not C not, and ABC. Unfortunately, we don't have an adjacent one, so we cannot simplify it using Carnot. So this will be our equation for Z. So the unsimplified is also the simplified. But we could do something about this equation. So kindly review your XOR and XNOR as logic. So if say XOR, we have X, XOR Y. The expanded version is XY naught plus X naught Y, while XNOR is just the negated version of XOR. Okay, so by having that knowledge, we could manipulate Z equation. Okay, so from this equation, let's factor out A naught for the first two terms and A for the last two terms. So this will be the result. And inside the parentheses, what can we say? This is the extended version of XOR and then XNOR. So therefore, let's write it using the XOR and XNOR gate. This will be the result. And by rewriting it using XOR and XNOR, the equation inside the parentheses, okay? So in this equation, we could see that it's also another XOR. So therefore, we could rewrite it as A XOR B XOR C. So by using our knowledge about XOR and XNOR, we simplified they from four terms with three variables, now three terms with three variables and one variable for each term. Okay, so using the Y and Z, now we could draw the circuit. And as you can see, we have the sub-circuit for Y, sub-circuit for Z, and we have one source for A, B, and C. So this will be the circuit that we're going to implement in the last stage of our designing our circuit. Now let's move on with our second example. So we're going to detect the number of ones. We're going to determine if it's even or not, including zero. Okay, so if it's even, 1. If it's 0, 1. Okay, so again, count number of ones. So how many inputs? 4. How many output? 1. Okay, since we're just going to detect if it's even number of ones. Okay, so this will be the truth table for our example 2. Again, as long as we have even number of ones, the output is 1, including 0, and the rest will be 0. Okay, so after determining the input, output, and truth table, so now we're going to simplify this circuit, this truth table. Okay, so using Karnaugh map, we're going to plot all midterms directly in our key map. So this will be the first, the 0, 2, okay. So after plotting everything, now we're going to group, but unfortunately, there are no adjacent midterms. So therefore, as is. So this will be our equation. Okay, so we have 8 terms with 4 variables for each term. But can we rewrite it using the XOR and XNOR? Probably yes. So let's apply. So I'm going to factor A naught, B naught on the first and second term. On the third and fourth, factor out A naught B. On the fifth and sixth, factor out AB naught. And then factor out AB on the last two terms. So this will be the result. And inside the parentheses, it could be either XOR or XNOR. So just apply our knowledge about these two gates. Rewrite the equation. So we have this. And as you can see, okay, we could factor a variable on the first two terms and also on the last two terms. So factor out A naught for the first two terms and A for the last two terms. So this will be the result. And inside the parentheses, we could also say that it could be either XOR and XNOR. So just rewrite it. Okay. So this will be the result. And A naught added to an XNOR, A added to XOR. This is XNOR. Okay. So this will be the result. So from 4 variables for each term, 8 terms in an equation. Now we only have 4 variables for each term, okay, and 4 terms only. Okay, so that's how we simplify this equation. So using the XNOR of A, B, C, D, this will be our equation. So it is more simplified compared with the original equation. Okay, so that's it for designing an equation. Designing a logic circuit. Okay, so thank you for listening. See you guys.